we start from Friedman equation with lambda term introduced by Einstein, and later he was not happy with it and said that it's a big mistake. But finally, this mistake is what we are observing now. So the solution of this equation in the case of a flat universe, flat means three-dimensional flat universe with zero velocity at infinity without lambda, gives you this simple solution, which has two important asymptotics. Asymptotics at the beginning is power law, and the asymptotic in large time is expansion. So this asymptotics actually is not to the very beginning, because we now it's accepted that at very beginning there was also stage, de Sitter stage like this, with lambda, which was many orders of magnitude larger, and it called inflation. But this inflation rapidly transformed into Friedman universe, and this is just Friedman universe. And we thought, most of us thought, that this Friedman universe is the universe in which we live now. But it happens that it is not so, and some small remnants of this lambda create this problem which called dark energy. This is what I already said, that its early stage is inflation with very large lambda term. Actually, it is not really Einstein lambda term. It's a term artificially produced by excited vacuum or scalar field or some other fields. And inflation is because lambda is decreasing very rapidly and decay to excited vacuum or excited scalar field to the stage of Friedman equation. And non-zero lambda term is transition from Friedman expansion to exponential stage, which is observed now. I must say that this is not the only interpretation of what is observed now, that it's de Sitter with lambda term. There are other approaches based on modification of Einstein theory, means when you have a Lagrangian with not with R under integral, but some function of R, and there are sometimes it's possible to find out such functions which mimic this exponential expansion. But the canonical interpretation is that it's lambda term. In order to measure this expansion, you need to know independently two values: the luminosity, the velocity of the object and the distance to this object. And when you have a distribution of velocities and distances in the cosmological scale, you may find out what law of expansion the universe has. And the most powerful sources of this, most luminous sources, are supernova. And among supernova, you need to have a very supernova which may be considered as a standard candle, because you cannot measure the distance. You should measure luminosity, and you should know what is the actual luminosity. And such actual luminosity gives you, if it is just something like standard candle, or you can have some transformation of to reduce it to a standard candle. Supernova type 1a are considered like this one, like such kind of objects. And supernova type 1a are the objects which created by the nuclear thermonuclear explosion. It's an explosion of carbon-oxygen core which lead to total disruption of the star. It's contrary to core collapse supernova, which produce supernova second type, supernova of type 1b, where there is a remnant in the form of the neutron star, and such supernova are very not similar to each other. There are big majority and of types of luminosities, and it's not possible to use as a standard candle. So the supernova type 1a is the one object which is observed, which is used. And here are some examples. This is in our galaxy. There were two last observed supernova were exactly supernova type 1a. It's Tycho supernova remnant and Kepler supernova remnant. It's a shell without central object. And so the luminosity is very high. So you can observe these explosions in a distant galaxies up to redshift approaching 1. And such program of observation of supernova in distant galaxies was realized in United States and Australia, and so several countries. There were two such observations, two such projects. One was by Rees and Schmidt, observational evidence for supernova in accelerating universe and the cosmological constant. This was the group which actually discovered this accelerating expansion of the universe. And another group was the group of energy department by Perelmutter Supernova Cosmological Project, which published a first paper in 97, where they claimed that there is no acceleration. The lambda is close to 0. But after another group has published it, they reanalyzed their data, used many more number of supernova, and also confirmed the result with better precision of the previous of this group of recent others. And finally, the diagram from which it was made a conclusion that the supernova is accelerating is this figure. You see here the data. It's a redshift and observed magnitude, distribution of magnitudes, and all these events are reduced to the standard candle. So suppose that they have the same luminosity. So this distribution can give you the indication how the universe itself is expanding. Not only because you know Z you find from the Doppler shift, but how it's produced, it is not clear because the distance is different. And here there are plots for different universes with different input of dark energy, and it happens that the best, statistically, the best plot correspond to lambda equal 0.7. So the total density is 1, universe is flat, and the input of dark energy is about 0.7. After this, you see it statistically not very visible from naked eye, but authors claim that it's statistically significant. So this result was obtained in 97, 98, and it was not completely accepted until the fluctuations, cosmic microwave background, have been observed by different instruments, and most important was the WMAP satellite. From this data, you also can extract the structure of the universe, and after making this extraction, the result was very close to what was observed by supernova, at least inside the error bars. So how you extract this data? This is WMAP distribution of fluctuations, and you see it is extremely non-uniform, and has a lot of additional noise connected mainly with galaxies, with other sources, and so on and so on. And so to extract a real signal, it is very difficult, as probably knows very well our chairman, but it was done. Next satellite, Planck, which is data of which have been published very recently, almost confirmed the data of WMAP. So they a little bit less omega instead of 0.7, 0.686, and also some small different, a little bit different Hubble constants, a little bit less than it was considered before, but I don't know how significant is this correction. So this is a Planck simulated one. So you have better resolution. You have better angular resolution. Therefore, you can go to larger numbers, wave numbers. So the perturbations, real perturbations of microwave radiation are correlated. It means that if you have two modes, decreasing and increasing, so in universe you have only one increasing mode, because the decreasing mode means that at the beginning you should have very, very non-uniform universe which contradict to present data. And when you have only one mode, for example sine, then if you come to the special place, for example recombination time, so different modes of different wave numbers come to this recombination time with different phases. And these phases, because it's a oscillating function, these phases also oscillate, and that means that the amplitude on the last on this level should be also oscillate. And these oscillations have been first predicted by Sakharov. So in Russia they called Sakharov oscillations. He considered it for another case, for a cold universe. Nevertheless, the main idea of coherent oscillation was done by him, and it's called, in other countries it's called acoustic oscillations in the West. So you have oscillational dependence of the amplitude of fluctuation on the wave number. And measuring the multiple and the height of this multiple, and also some properties of other harmonics, you can make a conclusion about different parameters, about omega, about Hubble constant, helium concentration, and the distribution between baryonic and matter and lambda, and so on. So this was WMAP. You see it's up till about 2000, and Planck has extended it to to higher, larger wave numbers. But in principle, the situation, the form is practically the same, and the numbers are also the same. So, as a result, we can conclude that what is now accepted, that we live in the expanding, accelerated universe where lambda, where the input of dark energy is about 0.7. And baryonic matter, which is concentrated in cluster of galaxies, has only 0.3. And even more, not baryonic, just ordinary matter. And baryonic matter, which protons, neutrons, and so on, only 0.04, which comes from deuterium concentration independently. When there is a clear the influence of dark energy into the expansion of the global expansion, there was a question raised first by Artur Chernin, who tried to understand what this dark energy influence on the structure of stationary galaxy cluster. Of course, the dark energy influence is only on very large objects where average density is approaching average density of dark energy. And the central part of clusters, as well as galaxy stars and all, have practically absolutely no influence of dark energy. Therefore, only large galaxy clusters can be influenced on this. And he made several papers trying to explain the Hubble flow in the local cluster by influence of dark energy, because the local flow is not should not be exactly the same as the global flow, but this similarity he explained by this influence of dark energy. And after that, we have with Artur also considered a problem of influence of dark energy into the structure of static clusters. So how dark energy changes the outer parts of the galaxy clusters. And there were two papers, this and this one. Here we considered just Virgo cluster, and next paper we considered Coma cluster. So the main parameter we determine the influence of dark energy is the radius of zero acceleration. This is the radius at which the gravity force is equal to zero, because sum of the gravitational force of the matter plus anti-gravity of the dark energy inside compensate each other, and so you have this radius, zero gravity radius. Knowing lambda, rho lambda from observations, we can put a maximum radius, because stationary cluster cannot exceed this radius. This is the maximum radius of the cluster. And it happens from some analysis that the radius of most rich clusters are close to this zero gravity radius. And so for Virgo cluster, it's about 10 to 15, and the radius is about 10 megaparsecs. And for Coma, it is less than 20, and mass is less than 5, 10 to 15 solar masses. And next step, which we have done with Marco Merafina from La Sapienza University, was to see what influence this dark energy produced for gas hot gas in the outer parts of the galaxy clusters. You know that hot gas form winds. We have solar winds, we have stellar winds, galactic winds. But observations show that in the galaxy cluster there is a very hot gas by X-ray observation with 5-10 keV, even more. And this gas, when it is expanded to outer parts, which are not visible because only density is very low, it can also form some winds from galaxy clusters. If it would be just wind, then it will not be too interesting because this adiabatic wind has decreasing velocity, as I'll show in a minute. But in presence of dark energy, this wind completely changes its properties and start to accelerate. So to investigate this problem, we solved the stellar wind equations, well known, with influence of dark energy. This problem can be solved here in Newtonian approximation because all velocities are much less than light velocity, and gravitational potential is much less than c squared. Therefore, in Newtonian approximation, the influence of dark energy is in this negative gravity term, where lambda is normal coefficient of Einstein coefficient. To solve this, you do it in the usual way. First, reduce the problem to non-dimensional coordinates, where presence of lambda lead to formation of one additional non-dimensional parameters, small lambda. Otherwise, it is the same equation which is usual for stellar wind, and this equation without lambda depends only on one parameter, gamma. Means when you have a polytropic equation of state, you have only one parameter at which depends this equation. So for each gamma you have one equation. But here, due to presence of additional parameters, for each gamma you have different, the family of equations. This system has a singular point. When you reduce it to one equation, for example, on velocity, you come to equation with a singular point, which is situated at the sound speed of the flux. It is transition from the subsonic to supersonic motion, like in the nozzle, in the rocket nozzles, like Laval nozzle. And Laval nozzle is produced by special form of cross-section. So in the minimum cross-section there is a speed velocity. But here the role of the cross-section plays gravity. So gravity produce such kind nozzle which can accelerate flow from subsonic to supersonic. And in addition, you have this term which changes the picture. So for example, the critical point without lambda is equal to 1. We choose C non-dimensional equal to 1 in the critical point. In the critical point. So R non-dimensional equal to 1/2. But here, presence of lambda changes considerably this situation. Here there are some exact solution of stellar wind which can be obtained only without lambda. With lambda you cannot. No, sorry. I'm sorry. I spoke about other things. This equation of motion. This equation of motion has one first integral called Bernoulli integral. Bernoulli integral is a just energy conservation integral. And you see that in addition to all terms, there is another term with anti-gravity. And presence of this term simplifies the outflow. And without this term, H should be positive for existence of the outflow. But in presence of dark energy, even for negative energies, of course, energy is determined, you should have a starting point, but at the same starting points, like without dark energy, you can have negative energy and you can have a still outflow. This is some estimation for lambda in the maximum interval. Lambda cannot exceed 18 for physically reasonable situation, and H should exceed this value. So when lambda is 0, H should be more than 0. This is a distribution of critical radius depending on lambda. Critical radius depend only on lambda. You see, it decreases, becomes closer to the center. I must say that here is, in this ideal case, I consider flux in the central mass, and the flux itself is not gravitating. It's not self-gravitation. And this is the radius of the extremum, radius of maximum effective potential. So this radius is always larger. And this is the function of Bernoulli integral as a function of lambda for three adiabatic, for three polytropic indexes. This is for 5/3. For 5/3, you have, in the case of usual stellar wind, you have a degenerate case where Mach number is constant and H is 0. So you have a 0 velocity at the infinity, and accretion and expansion follow the same line. But in the case of other smaller gamma, you have positive value of H. This is for 3/2. This is for 4/3. And when lambda increases, you can have a solution with negative lambda. Here are several analytical solutions which I will not discuss. And this is a numerical solution which was obtained in the usual way. When you have a singular point, you should start from this singular point, make an expansion in this singular point, and then go up in two directions from this point by integration, making first step analytically, and then you have a full solution for accretion, for wind, and so on. So these are coefficients which we have when we take into account non-zero lambda. In the case of usual outflow with lambda 0, you come to well-known expansion which is used for stellar wind. But here it's a more complicated case, but nevertheless it's not so interesting. So you see that with the finite lambda, the solution exists for different gamma, even more than 5/3. In the case of 0 lambda, 5/3 is a limiting case, because when you have a larger lambda, the flux is cut at a finite distance, and it cannot be realized, cannot go out to infinity. But in the case of presence of lambda, you can have formally until infinity, but Of course, it's not so. So these are the solutions are found here. You see, these solutions are perfectly one line, but the way how they were obtained, I described earlier. From this critical point, I started a step here and then calculated one program. This is another program calculated this one. And you see that this perfect fit because of very good treatment of the singular point, and you have a continuous solution. Sometimes people try to calculate stellar wind without expansion, and in some cases they succeed, but in most cases it is not so good. So this is for gamma equal 4/3, and for different lambda. This is lambda 0. You see, at lambda 0, the flux is not practically not accelerated over the singular sonic point. This is lambda 1. You can accelerate it 5 times, and at larger r. And for lambda equal 5, acceleration is even larger. And here you join Hubble expansion, so velocity is increasing proportional to radius. This is the same for gamma equal 3/2. For gamma equal 3/2, the solution, outflowing solution, has constant velocity. You have constant velocity with increasing Mach number because the temperature is decreasing. But in the case of non-zero lambda, you have also acceleration. Here also accretion solutions are indicated. This is accretion solution. But accretion solutions are different at large distance, but at the inner region, inside sonic point, they merge, and practically dark energy has no influence on accretion. And this is the most interesting case of gamma equal 5/3. Why 5/3 is most interesting? Because outer parts of the cluster are so rarefied that practically they don't emit anything. And so it is just the flow of adiabatic flow of non-relativistic gas which has adiabatic index of 5/3. In the case of 5/3, the velocity with constant Mach number is decreasing, you see. And in the presence of dark energy, velocity is increasing considerably. Therefore, we may expect that in presence of dark energy, the outflow from galactic cluster have absolutely different structure compared to the absence of dark energy. Here are the estimations to the coma cluster. In the case of coma cluster, as you remember, we had R less than 20 megaparsec, but I used 15 megaparsec here with 5, 10 to 15 solar masses. This is density of dark energy measured, corresponding to 0.7 lambda. And the small parameter lambda, small lambda, is 0.6, almost 0.6, with velocity 1,200 kilometers per second, corresponding to kT 5 keV. This is very moderate estimation. You can have even more. You can have 10, 11, 14, some indications. Therefore, this is not the case of limiting case. It's an average case. And this is solutions directly connected with these parameters. Even for lambda equal 0.58. This is for larger lambda. So this solution describe the galactic wind from the coma cluster. If there is such a high temperature gas outside, but we know that it should be there. And so you see the difference of velocities here increasing, and it may be larger 3-4 times. So this is the solution which describes the galactic wind from the coma cluster where temperature in the critical point is 5 keV. And you see that the velocity may be several times larger than virial velocity in principle. And this is very important. So here it's written what is the influence I expect. So after quitting the cluster, the gas is moving with acceleration, acting as a snow plow for the intergalactic gas. It combines a lot of matter. The shell of matter forming in such a way may reach a high velocity exceeding the speed of galaxies in the cluster. So this shell can move with speed larger than virial. If the shell meets another cluster or another shell moving toward it, then the collision of such flows may induce a particle acceleration. So they definitely make particle acceleration. But in this case, due to high speed, large size, and low density, such collisions may create cosmic rays of the highest possible energy. Yes, I'm coming to that. And we may expect the most larger effect when the two clusters move to each other. So the main observational conclusion from here is that we can expect collisions of such winds, and in these winds we may accelerate particles in principle up to the highest energy, up to the limit of Zatsepin-Grazin-Kuzmin, which is impossible in the present situation. The people who made this, they cannot accelerate. But when you increase density, velocity several times, you can reach it. What is important is that the influence of dark energy is decreasing with the redshift. When you have at high redshift, the galaxies are close to each other, and you can have such a big scales, and at small scales, you don't influence of dark energy is low. So the acceleration of extra high energy cosmic rays in this model should take place in the periphery or between the closest rich galaxy cluster. So this high energy, very high energy cosmic rays should be created not very far, but in the vicinity with a Z less than 1, like this. This is only the example that the collisions of galaxy cluster exist in reality. This is observation. Interpretation is quite, in my opinion, artificial. They say that this dark energy goes through each other, and plasma form shock wave which remaining here, but
dark matter goes through each other.
Yeah, dark matter, yes.
You said dark energy, but you meant to say
sorry. You're right. Of course, it's dark matter, of course. Dark matter goes through. In this case, dark energy influence is negligible because the scales are low. But this is an example of collisions, an example that this may be indication that the outflow exists. Because if it's not the case when they go through, but just two winds coming to each other, so this is just a result of wind collision. It's just another interpretation. I don't want to see that it is correct or not correct. So instead of penetration of dark matter through each other, it can be just two colliding winds. And this is calculations of colliding winds made for stars. While Fourier star is colliding with the wind from supergiant, and it forms also such a shock wave. So in principle, the problem is similar. And you see you can find some similarity. And this is the just description of the Zatsepin-Kuzmin limit. At high energy, you produce pi 0, which cut this, and you cannot have such objects from the distance larger than 50 megaparsecs, which is not enough. And so what I say, this is a cosmic ray spectra. What I'm saying is that this vicinity, the usual theory using virial velocity can explain only up to this somewhere here. But this tail cannot be explained, and maybe accelerating winds can explain this tail. And so the parameters of the cluster, Virgo cluster, is about 17 megaparsecs. Compact cluster is distance to the Virgo cluster. Compact cluster is 100 megaparsecs. Able cluster is 170 megaparsecs. So these scales are enough for having such a high velocity wind. So the conclusion is the following. So the density of dark energy measured from supernova distribution and fluctuation of CMB perturbation imply the necessity to take into account the structure of the outer parts of the galaxy cluster. The existing observational undefiniteness in the parameters indicate the dynamical importance of dark energy in the scale of galaxy cluster. And hot gas in galaxy cluster is accelerated in presence of dark energy, and extra high energy cosmic rays may be accelerated in rapid colliding winds from cluster moving to each other. So it is, of course, if the cluster expand pure Hubble low, then the collisions are ineffective, because we should have a cluster with large peculiar velocity which move preferentially to each other. Thank you very much.